So if you cannot see your exam grade, please let me know as soon as you can. But you should be able to see them. They should be in the grade book as well. I've been having some issues in other classes with grades that I've posted not appearing in the grade book, which is very strange. Um, However, they are definitely in my grade book, and I can see them on D2L, and you should still be able to see the grades and the feedback in the assignment screen regardless. So if you have any questions about grades and feedback and anything like that, please let me know, and we can talk about it. Sorry, these grades were a little bit late, but hopefully they're out of the way now. Generally, the grades were very, very strong for this test, which is expected since it was a, you know, fully open note test. So, um, anyways, today is sort of our last day of new content. We're going to do a little bit of new stuff today. I'm hoping that we can get through a bunch of stuff. We'll see how far we get. I'm not going to go too much more than an hour here. So we'll do our best to get through the stuff I want to get through. And today I kind of want to talk about some properties of conics. And the conic I'm primarily interested in the property of here is ellipses. Um, and in particular, so properties of the ellipse. So the ellipse is sort of that sort of skewed circle. It's sort of stretched out a little bit, and we know that an ellipse has an ellipse has a center. So some point in the middle, and then it has a major axis, and then it has a minor axis. So this here is the major axis. This here is the minor axis. And then the ellipse is kind of like this almost egg or football shape. Maybe not quite so egg shaped. It should be symmetrical. So ellipses also have two extremely important points on the end. These points are called actually, let's even put them in a different color. These points are called the foci, um, which is plural for focus. Um, Sometimes I'm going to say focuses because foci is a weird plural, but I think the correct plural is technically foci. And the foci are really important. They're actually more important than the center of an ellipse when it comes to the construction. Okay. So if we think about for a second a circle is sort of like an ellipse that doesn't have a major or a minor axis. Both axes are sort of the same length. And in some sense, a circle has foci as well. It's just that in a circle, the distance between the foci, or the distance between the center and the foci, is 0. So the focus and the center coincide with each other. And some of you may have seen this before, but there is a way to um, draw a circle using a pin and string. So, real quick, it kind of looks like this. Notice he's putting the pencil inside the string there. and then he's using that to maintain that radius, right? It has the same radius to every single point. That's sort of what the definition of a circle is. So the definition of a circle is a center, or is every point in the plane. This is the geometric definition of a circle, obviously not the conic definition of a circle, but it's every point in the plane equidistant from a fixed point or center. This is how Euclid, of Euclid's Euclidean geometry, defined the circle. The ellipse sort of has it has a similar property, but it's not exactly the same. In an ellipse, we have instead of just having one distance, any point on the edge of the ellipse has two distances. We'll call this D1 and D2. So in an ellipse, the sum of the distances from any point to each focus is the same. So instead of being the collection of points that are equidistant from a single point, an ellipse is the collection of points that the sum of the distances to two fixed points is the same. And this actually gives us a method of drawing an ellipse. What you can do is instead of have one pin and one string, you can have two pins and a string that goes between them with some slack. And then you cannot see what I am writing. I apologize. I forgot to switch back. So in an ellipse, the sum of the distances from any point to each of the foci are the same. So D1 is equal to D2. Or sorry, D1 plus D2 is constant. So what you can do with an ellipse is you can take two pins and a string with some slack between them, and you can sort of nestle your pen in the nook of the string, and then use that to draw an ellipse. I also have a video of that real quick that I can show. So notice how he has a pin on the right-hand side and a pin on the left-hand side. And then he's going to draw the ellipse with the taut string. So notice how he has the two pins, and then the string sort of, or the pen sort of nestled in the string there, and that makes a perfect ellipse. What this definition actually allows us to do is it allows us to find what's called the focal length, and to locate the foci of the ellipse. Let me change my color back to black here. So the focal length of an ellipse, the focal length of an ellipse is called, we're going to call it C, is the distance from the center to a focus of the ellipse. Alternatively, it is half the length between the two foci. So if we go back up here, this ellipse had a center in the middle here, so the focal length might be 2, and the distance between the two focuses was 4. The foci always lie on the major axis. Okay, so they're always on the longer of the two axes. You never have foci that are on the shorter of the two axes. And we're going to consider, so from here on, we'll consider only horizontal ellipses. So ellipses with horizontal major axes. Just to simplify our notation a little bit. So let's take an ellipse that has a horizontal major axis. So maybe something along these lines. Hold on. I probably don't need to be such a perfectionist with this ellipse, but here I am. Being kind of a perfectionist about the ellipse. Whatever. That's good enough, right? And we have a couple of important things to label here. So here is our minor axis. Then here is our major axis. And then maybe our focus is somewhere around here. How do we actually find this length between the center and the focus? Well, if we know where the focus is, we can measure it, right? But let's say we don't. Well, we know, for one, that if we hold on. If we take any point on the rim of the ellipse and we measure the distances from that point to each of the foci, then that distance has to be some constant. So can we find what that length actually is? And it turns out that we can. If we pick this point here, which is the point that lies on the major axis, also called a vertex, of the ellipse, then we get D1 here as the distance from the vertex to the first focus. And then we get D2 here, which is the distance from the vertex to the second focus. Notice that this is the entire breadth of the ellipse, right? Except for just this area here, this little length over here on the left-hand side. But we copied this little length over here. This is the same length as D1. So what this tells us is that these two distances, D1 and D2, for the point, the vertex here, they have to be the length of the major axis, or 2A. So if we then pick another point up here at the very end of the minor axis, this is actually called a covertex, then we again get two distances. We'll call this D1 prime and D2 prime. But these two distances, because this is an ellipse, they're the distance from, one of them is the distance from the right-hand focus to the point on the ellipse. The other one is the distance from the left-hand focus to the point on the ellipse. They must also be the same as the initial two lengths to add it together. So D1 prime plus D2 prime is also equal to 2A. But here we see two triangles, right? There's one triangle on the right-hand side and one triangle on the left-hand side. And these two triangles are isosceles. Or rather, these two triangles are congruent. Another way of thinking about it is that the triangle formed by the two foci and the covertex is an isosceles triangle. It has two sides of the same length. So that tells us that D1 prime is equal to D2 prime. So that means that D1 prime, or let's use D2 prime here, is equal to A. In other words, this length here from the focus to the covertex is the exact same length as the distance from the center to the vertex. And because this is a right triangle, we can use the Pythagorean theorem in actually what's a really annoying application of the Pythagorean theorem. Remember that this length here, this red length, was B. This blue length here was C. And the green length is A. So this gives us an issue in that A squared is equal to C squared plus B squared. Or C squared is equal to A squared minus B squared. And this applies when the major axis has length 2a and the minor axis has length 2b. And that's how we find our focal length. We don't have to go through all those steps. We can just apply this formula. Remember that a and b are in the equation for an ellipse. So, for example, find the focal length and locate the foci of the following ellipse. X squared over 25 plus y squared over 9 is equal to 1. So this is actually the ellipse I drew earlier, up above. And note that this is a horizontal ellipse. So of the variety x squared over a squared plus y squared over b squared equals 1. So that means that a squared is equal to 25 and b squared is equal to 9. If you prefer, a is equal to 5 and b is equal to 3. So c squared is equal to a squared minus b squared, which means c squared is equal to 25 minus 9, which is 16. So c is equal to 4. So our focal length is 4. If we go back up to our drawing up here, you can see that as well. The major axis had length 5. 1, 2, 3, 5. The minor axis had length 3. Well, technically the minor axis has length 6. B is half of the minor axis. Similarly, the major axis has length 10. A is half of the major axis. And then that means, and our focal length ended up being exactly 4. Though, if you do remember, I did actually place the focuses before saying anything about the focal length, so this isn't exactly a proof. Though what I did is technically a proof. A little bit of a messy one, but here we are. Does anybody have any questions about finding this focal length in the ellipse? Okay, so there's one more question that we have to answer here, which is, so we found the focal length, but we also need to locate the foci. So the foci lie along the major axis, a distance of c away from the center. So our ellipse was x squared over 25 plus y squared over 9 is equal to 1. So our major axis is the is horizontal. The bigger number is under x. So we know our ellipse is horizontal. And our center is at 0, 0. There's no x minus anything. There's no y minus anything. So it's the same thing as saying x minus 0 squared, y minus 0 squared. So that tells us where our foci are. If we sort of draw our graph, I'm not even going to draw the ellipse into it. Our center is here, and our major axis is going to be horizontal. So we need to go a distance of 4 out to the right and 4 out to the left. 1, 2, 3, 4. 1, 2, 3, 4. So our foci are the points 4, 0 and -4, 0. So foci are at 4, 0, -4, 0. So that's a ton of geometry to find this focal length, and I haven't told you any reason why you should care about what the focal length represents. And finding the focuses of the ellipse can actually be really important, because there's a couple of really important properties of ellipses that have to do with the focal length. In particular, the first one that I want to talk about is the reflective property of an ellipse. So the reflective property of an ellipse um, basically what it says is that if we have a like this pool table above, so this guy has a really weird looking pool table. It doesn't have holes at the corners. It doesn't have any corners. It is an ellipse. It's not quite circular if you look really closely. And the cue ball is placed at one of the focuses of the ellipse, and the pocket is at the other focus of the ellipse. And the reflective property of the ellipse, and I'll write this down in just a second, what it says is that if you reflect a ray off of any point from one focus, off of any point on the edge of the ellipse, it will always reflect directly back to the other focus. And we can watch this in action. So watch him take this shot here in 9 different places. So you'll notice that in every single one of the cases, he did a perfect bank shot, and it landed almost exactly in the hole. So we can watch that again real quick. There's a little bit of bouncing around. You'll notice that, like, for instance, one of the balls is a little bit to the right of the hole. Some of them were right on, some of them were a little bit to the left. Um, that has to do with the unfortunate reality of physics in the real world. I'll post a link to this video after lecture so you guys can watch it. He explains it a little bit, but basically what's happening there is that the edge of the pool table has a little bit of flex to it. So when it bounces, if he shoots it really hard, the angle isn't quite right, and if he shoots it really softly, the angle isn't quite right. But in general, this really, I think, well demonstrates the reflective property of an ellipse. So the reflective property of an ellipse is that any ray that starts at one focus and reflects off the ellipse will be directed towards the other focus. So in other words, if we have our ellipse here, I should make a slightly bigger one. And it has maybe focuses here and here. If I start at one of the focuses and then I bounce off the edge of the ellipse, I'll always end up pointed directly at the other focus. This doesn't just have applications to novelties, though some of the cutest applications are for novelties. In fact, another application is that like some cathedrals and museums have rooms like this. But if you stand in an elliptical room, even if it's a really crowded room, if you stand at one of the focuses and your friend stands at the other focus of the room and you guys whisper, you'll be able to hear each other as if you were right next to each other, because what's happening is the elliptical shape is bouncing every single sound wave that you're outputting off of the walls in such a way that they're heading exactly to the other focus, right? So every single sound wave gets focused back to the same point, so it sort of sounds like they're very, very close. Um, Another application of this is in treatment of kidney stones. So a kidney stone, you have like a mineral deposit that happens in your kidneys, and what they do is they place a actually a hyper, like a very very powerful sound wave emitter that sits at the one focus of an ellipse, and then they place you such that the kidney stone lies at exactly the other focus of the ellipse inside a big elliptical reflector. And that what that does is that means that every single sound wave that bounces off of the reflector is going to head to exactly the kidney stone, which then causes it to break up and hopefully be able to be passed. Um, so basically, what this means is that in order to know how to apply this reflective property of the ellipse, in order to be able to place these things correctly, you need to be able to find the focuses. So finding focuses is important for these applications. Without it, you wouldn't know where to place the patient and the emitter so that the kidney stone can be properly um, reflected or can be properly disposed of. You wouldn't know how to build that stupid pool table. You wouldn't know how to design the room that you can hear people from across the room. Um, any of these things require finding the focus of the ellipse. The other property of an ellipse that is important and has to do with the focal length is called eccentricity. So eccentricity is actually a property that applies to all conics, but we're not going to talk about how to compute eccentricity for hyperbolas. We just don't have time to deal with it. But eccentricity denoted as E, which is annoying because for us E is Euler's constant. This is 2.71828. In the context of conics, E stands for eccentricity, not Euler's constant. Euler's constant doesn't really show up much in the study of conics, so E was a little bit free. But it measures, so eccentricity is a measure of how skewed a conic is. If you have an eccentricity of 0, then you're a circle. So the least eccentric conic, an eccentricity of 0, is the circle. It's not skewed at all. It's pretty much just absolutely straight, right? And then as eccentricity grows, the circle starts to stretch out. So if your eccentricity is between 0 and 1, then you have an ellipse. An ellipse with very small eccentricity is very circle. Is very circle. That doesn't make any sense. Is very circular. If E is close to 0, then the ellipse is nearly circular. If E is close to 1, the ellipse is very stretched. So E being close to 0 means that maybe it's just barely an ellipse, right? It almost looks like a circle. It's very, very close, right? E being very large means that, well, very large. E being close to 1 means that your ellipse is very skewed. It's much wider than it is tall, or much taller than it is wide. So if your eccentricity is equal to exactly 1, then you're a parabola. So basically, you can kind of think of this as the ellipse becomes more and more and more and more skewed, basically eventually it's going to break apart at the ends. Like it essentially, if your minor axis is some fixed length and you're making your major axis bigger and bigger and bigger, stretching it and stretching it and stretching it, if that becomes sort of infinitely large, eventually it's just going to turn into a parabola. The two ends will never come back together again. And if you go beyond that, if your eccentricity is bigger than 1, then you have a hyperbola. So in an ellipse, E is equal to the focal length divided by half of the length of the major axis, or C over A. So essentially, if your focuses are very, 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 very close to um, the middle, if your focuses are very, very close to the middle, then you'll have a low eccentricity. But if your focuses are very, very, very close to the vertices, then you will have a high eccentricity ellipse. So one place where we use um, the eccentricity of ellipses is when talking about actually orbits, right? If you go look up a particular orbit of some sort of celestial body, like the like Earth or Mercury or something like that, typically there'll be a bunch of lists of different statistics about it. Um, one of them um, will be the eccentricity of the orbit. So, for example, um, the dwarf planet Pluto has a fairly eccentric orbit. Some of you may remember Pluto being a planet, actually. At least when I was a kid, we were taught there were 9 planets. The last one, the furthest one from the sun, is Pluto. But Pluto is very problematic as a planet, which is why it got demoted. One of the biggest problems with Pluto is that it's not always the furthest planet away from the sun. Sometimes Pluto is closer to the sun than Neptune is, um, which is super problematic. Um, it's also there's a bunch of reasons why it ended up not being a planet anymore. It ruins a lot of other nice symmetries about the solar system, and it's very similar to other planets. We would have had to start adding more and more planets if Pluto hit those guidelines. So we ended up cutting it. But Pluto has an extremely eccentric orbit for a planet. It has with an aphelion of 49.305 AU and a perihelion of 29.658 AU. These words and terms and units, I don't expect you to know off the top of your head, so let's talk about them really quickly. So, sort of in a sidebar here. So, first off, dealing with the units, 1 AU. This is called an astronomical unit, but it's equal to the average distance between the Earth and the Sun. Um, Basically, the problem is that in like in astronomy, the scale is so large that if we were to just use like kilometers, all the numbers would be tremendously huge. But at the same time, something like a light year is too large. If we tried to use light years to express distances within the solar system, all of our distance would be incredibly small. So we use astronomical units as a way of sort of saying like on a scale of like how far is it from us to the sun. Okay, that's the measuring mark we're going to use to sort of detail all of these distances within the solar system. It's called an astronomical unit. So aphelion, the aphelion of an orbit is the distance of the farthest approach from the sun. In other words, in the orbit, what is the furthest away from the sun that Pluto gets? Well, it's about 49.305 times as far away from the sun as the Earth is on average. And predictably, perihelion is the same, but it's the closest. So the aphelion is the furthest away from the sun that Pluto gets, 49.305 AU, and the perihelion is the closest to the sun that Pluto gets, 29.658. For what it's worth, Neptune is typically, so the aphelion of Neptune, which is the eighth planet, the furthest planet from the sun, is 30.33, and the perihelion of Neptune is 29.81. So Pluto doesn't spend a lot of time closer to the sun than Neptune does, but sometimes it's much, 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 much further away. Or most of the time, it's much further away. So planets have an elliptical orbit with the sun at one focus. So maybe the sun is here. Then maybe this is Pluto's elliptical orbit around the sun. And it turns out that really conveniently for us, the perihelion occurs when Pluto is at one of the vertices of the ellipse, and the aphelion occurs when Pluto is at the other vertex. So this lets us start computing some things. So this means that the length of the major axis of the ellipse the length of the major axis of Pluto's elliptical orbit is 29.658 plus 49.305, or or 78.963 AU. So A is equal to 78.963 over 2, which is 39.4815. And we don't know what B is, but we can also use this to determine what C is, because C is this distance here. If we do, so the distance from the center to Pluto at its perihelion is 39.4815. And the distance from the sun to Pluto at its perihelion is 29.658. So that tells us that the distance from the sun to the center, or the focal length of the elliptical orbit, is 9.8235, and that's our C. We know that from our focal length formula that C squared is equal to A squared minus B squared. So B squared is equal to A squared minus C squared. So B is equal to the square root of 39.4815 squared minus 9.8235 squared. Or about 38.24. Let's round that one more place. 240 AU. So if we want to model this as an ellipse that is orbiting around the sun, centered at 0, 0, the sun is not going to be at 0, 0, but the center of our ellipse will be at 0, 0. So an equation for this ellipse is x squared over 39.4815 squared plus y squared over 38.240 squared is equal to 1. And the eccentricity of this ellipse is equal to C over A, which is 9.28235 divided by 39.4815, or about 0.24 or 0.2488. Mercury also has a very eccentric orbit, but the eccentricity of Neptune, for instance, is 0.009, and the eccentricity of the Earth the eccentricity of the Earth's orbit is 0.0167. So Pluto is significantly more eccentric than the Earth is, more than 10 times as eccentric, more like 15 times. Okay. As much as I want to just barrel onwards and talk about parabola properties, we don't have time. And I'm not going to make you sit here and listen to me for even longer than you already have. So this is where I think we're going to end the semester. Well, we have one more class still for review, but this is our last. This is the last new content. We will not talk about the reflective property of parabolas, which is kind of a shame. So our only applications in this unit will be applications of ellipses. So when I give out things like, I have a midterm from last semester that I'll hand out, and I also have I'll hopefully have some review stuff. We will skip anything on parabolas. So, does anybody have any questions about the orbit of Pluto here, our example? Either finding its eccentricity or finding the equation of the orbit itself, given the information. Okay. In that case.